We continue our discussion of GOES imagery and data in this module, which focuses on the long-wave bands. Remember the second idealized case covered in a previous module. It related to passive remote sensing of IR radiation emitted by both the surface and along a path through the atmosphere to a satellite. We ended up with two terms to describe the radiance at the top of the atmosphere. The first described the percentage of radiation emitted by the surface that was not absorbed by the atmosphere, and the second quantified the total radiation emitted along the path at the wavelength of interest, which is a function of the atmospheric temperature and optical depth profiles. Ultimately, emissions observed at a satellite are a summed combination of surface emissions, if any, and emissions occurring at various temperatures throughout the depth of the atmosphere. And that's what this picture over here is trying to capture. We're not concerned about scattering of infrared by air molecules in a clear sky environment. However, clouds, especially physically thick ones, do scatter some IR radiation. Liquid water and ice also absorb IR radiation. Let's return to our plots of spectral response functions. In this module, we turn our attention to the bottom row and focus on the SRFs for IR bands on GOES. The bands are generally wider than for the shortwave bands. This is required since in general, long-wave spectral radiance is less than that at shorter wavelengths. Therefore, wider bands are required to achieve the desired spatial resolution. The red line denotes the average brightness temperature as a function of wavelength given standard vertical profiles of temperature and humidity. Higher infrared brightness temperatures, which are the bottom of the axis, correspond with higher atmospheric transmissivity. The brightness temperature is the temperature that a black body would require to emit the radiance observed by a satellite. Consider the expression for Planck black body radiance, which is a function of wavelength, right here, and temperature. By rearranging the equation, we can easily derive an expression for brightness temperature that is a function of top of atmospheric radiance and the wavelength. An example of brightness temperatures for a band in the IR atmospheric window is shown here. This is an example of enhanced image. The colors indicate objects, often clouds, that have the lowest brightness temperatures. Darker colors indicate warmer emissions, such as over here in the desert southwest. Since temperature generally decreases with height in the troposphere, the darker regions correspond to emissions from lower in the atmosphere or even the surface. An unenhanced image would simply replace the colors with various shades of gray and white, with the brightest whites denoting the lowest brightness temperatures and the dark colors, the blacks, still indicating the highest brightness temperatures. Another example, which is down here in the Atacama Desert region. A couple of things must be considered when interpreting brightness temperatures. First, the emitting body might not be a black body. However, for infrared radiation, we will usually approximate the surface and clouds as black bodies for the purposes of discussion in this class, meaning that epsilon can be approximated as 1. For a particular wavelength, sometimes emissions by liquid water or other molecules isn't quite 1, and GOES ABI takes advantage of this fact in determining which bands are used for various products. When epsilon is approximated as 1, this means that a lower IR brightness temperature generally corresponds to a lower actual temperature. When we discuss microwave radiation later in the class, we will see that surfaces can emit much less than black bodies, which greatly alters the interpretation of brightness temperature. Second, extinction of radiation could occur as it propagates upward through the atmosphere. Furthermore, the rate of extinction may change with height. Therefore, the brightness temperature observed may be representative of radiation emitted from various different altitudes, including the surface. The vertical derivative of direct transmittance is known as the weighting function, which will be covered with more detail in the next module. Now, returning to our plot of SRFs, we see that some bands, like 8, 9, and 10, sit in parts of the spectrum where average brightness temperature is low. The brightness temperature is low between roughly 5 and 8 microns because water vapor absorbs radiation of these wavelengths. Thus, much of the radiation emitted by the surface at these wavelengths gets absorbed as it passes upward through the atmosphere. Whatever object that absorbs the radiation then re-emits radiation, but it preferentially does so at a wavelength consistent with its temperature, usually a slightly longer wavelength since temperature generally decreases with height in the troposphere. Next, let's step through each band individually on this bottom panel. First is band 7 at 3.9 microns. It is a short-wave infrared band and is the only GOES band that routinely observes overlap between reflected solar and emitted terrestrial radiation. Generally, the radiance observed is converted to brightness temperature for display. This daytime image in band 7 displays high clouds as black. While they may be cold, they are also reflective of solar radiation. The shortwave IR is particularly useful for fire identification, similarly to band 6. It is also useful for detecting small ice crystals because they are more reflective of radiation at this wavelength. This increases the radiance of the sensor, making the cloud appear warm, so to speak. This is why the high clouds appear as black in this image. Larger ice crystals are not efficient at scattering 3.9 micron radiation, therefore they appear as cold. Bands 8 through 10 are the water vapor bands. As stated before, the bands are located in a region of the EM spectrum where water vapor absorbs. That means that the horizontal variability in brightness temperature observed in these bands is caused by a lateral variability in the vertical distribution of water vapor. These channels are best interpreted as a group. Using the same color scale, we see many more red and orange colors at band 9 except for where high clouds are present, such as over California or the offshore coast. And the brightness temperature is even warm for channel 10, with brightness temperature much closer to 0 degrees C in some places, as denoted by the red shading. And the scale is shown down here, although it's a little bit difficult to read. This is 0C, where my mouse is now is 5C, 10, 15, minus 5, minus 10, minus 15, minus 20, minus 25, 30, and so on. When we compare the three alongside each other, when using the same color scale, it becomes clear that the average brightness temperature of the same scene generally increases moving from band 8 over to band 9 and then 10. This is consistent with the graph in the bottom left, in which brightness temperature increases going down on the y-axis and is therefore greater in band 10 than in bands 9 or 8. This means of the three, band 8 is most susceptible to absorption by water vapor in the atmosphere. Emissions from the surface at 6 micron wavelength, which is about right here, are less likely to penetrate to space than the 7 micron radiation over here, or 7.5 micron radiation. Therefore, in band 8, we see more emissions from high in the atmosphere, and thus the brightness temperature is generally lower. In very dry areas, the difference in brightness temperature between the three bands will be less. It is not unusual for a particularly dry column to yield a brightness temperature of as high as even 0 degrees C in band 8. The brightness temperature of the three bands in a region of thick clouds, however, will be very similar because few emissions from beneath cloud top reach space at any wavelength in this part of the IR spectrum. We will not discuss channel 11 all that much in this class, but the 8.5 micron band is situated partially in an absorption band for sulfur dioxide, which is emitted by volcanic eruptions, making this channel useful for detecting volcanic ash. Now, this is not an example of that case, of course, because there's no volcanic ash in this scene. Otherwise, the atmosphere is mostly transparent to this radiation. Also, the emissivity of liquid water is less than 8.5 microns than at other bands in the atmospheric window. Therefore, this band offers another way to detect the phase of water in clouds. Another band, channel 12, sits in the middle of the ozone absorption band. You can see immediately how the brightness temperature in band 12 is generally lower than other bands. This is because ozone emissions in the lower stratosphere occur at a level where the temperature is colder than much of the troposphere. However, in deep convection, band 12 brightness temperature can be higher than in an atmospheric window channel that is not sensitive to ozone because the lower stratosphere is warmer than the upper troposphere. Channel 13 at 10.3 microns is the least impacted by absorption by atmospheric water vapor. Therefore, it is most commonly used for 24-hour surveillance of clouds. This is one of the channels that is akin to the legacy infrared channels on old GOES platforms. Remember, the brightness temperature is not necessarily temperature. The high cloud seen over California and offshore is obvious in this imagery. And the brightness temperature of the cloud ranges from roughly minus 10 to minus 30 degrees C. However, some of the cloud may actually be colder than indicated by the brightness temperature, especially if it is physically and therefore optically thin. Thin cirrus clouds often allow surface radiation to penetrate through them, meaning that radiance detected at the satellite sensor is caused by some combination of emissions at the top of the cirrus cloud and emissions from below, which is exactly what Shortall's equation says we should expect. Channel 14 is similar to 13, but experiences a little more absorption by water vapor at 11.2 microns. It can generally be used for the same purposes as Channel 13, but the two together can be used to assess atmospheric water vapor concentrations. And finally, Channel 15 at 12.3 microns also sits in the atmospheric window, but experiences a little more absorption by water vapor. The split window difference can be calculated using channels 13 and 15. It is just the difference in brightness temperature between the two channels. This difference increases as atmospheric water vapor increases because channel 15 is more susceptible to absorption. Emissivity of dust and ash, however, is lower at 10.3 microns, so the brightness temperatures will actually be larger in channel 15 than in channel 13 in areas where such aerosols are present, depending on the water vapor concentration. This could make the split window difference potentially be negative. Band 16 will not be used much in this class either. It sits on the edge of a broad carbon dioxide absorption band. Brightness temperatures will generally be cooler in channel 16 than in the center of the atmospheric window where the SRFs for channel 13 through 15 are situated. Brightness temperature from this band is also used to generate many post-processed satellite-derived products.